Hello everyone, this is Professor Lee again. So today we are going to talk about probability in chapter 3. So this is a brand new chapter, right? Up until chapter 1 and 2, we were discussing several different topics in statistics. Now from chapter 3, we're going to switch gear and we are going to start a probability chapter, right? Probability chapter. So this chapter 3.1, basically we are just going to deal with several basic terminology and basic concept in statistics, in probability. Even though this is a very basic, we all know this is very important that we actually understand all the basic in order to learn a proper the more challenging content here, right? So today's class is very important that we understand the basic concept in probability, right? So probability, what is it? Probability is a measure, meaning at the end, probability is just going to be a number that describes something, that associate with how certain we are of outcomes of particular experiment or activity. Or something like this. If you flip a coin, what's your chance that you are going to get either head or tail? You know, when you roll a die, what's your chance that you get number, for example, 5, right? At the end, it's just going to be a number. Probably it's a number that associate with how certain we are of some type of a particular experiment. Now, this is also a technical term, right? So when we say probability experiment, it's just right here. An experiment is a planned operation carried out under controlled condition, right? Meaning the action of flipping a coin, that's an experiment. The action of rolling a die, that's an experiment. The action of choosing a card from a deck of playing card, that's an experiment, right? So for now, so far, probability is a number. Experiment is the action of either choosing, flipping, tossing, rolling. That's an experiment, right? And if the result is not predetermined, it's not really, when you flip a coin, the result is not predetermined. It could be head, it could be tail. It's not determined yet. So that type of experiment that's not predetermined is what we call chance experiment, right? So something like a flipping a fair coin twice or once in the same way, it's an experiment. And we call that particularly chance experiment because the result is not fixed yet, right? Okay. All right, let's go to the next page. Let's talk about sample space and outcome. Now, result of experiment is called an outcome. Remember, the action of flipping a coin, that's an experiment. So think about it. When you flip a coin, what will happen? If you flip a coin, then you are going to get either head or tail. So each result, head or tail, each individual result is called an outcome, right? either H or T. These are both outcome. Okay, then what's a sample space then? Sample space of an experiment is set of all possible outcomes. So if you collect all possible outcomes, that's a sample space. So when you toss a fair coin once, your sample space, they usually use S for sample space, is going to be either head or tail, right? Head or tail. Now let's say you're rolling a die. You know the die that looks like, I don't know, it looks like this, right? It looks like this exact cube that you have this one dot, you have two dot, you have three dot, and you have all six dot in this cube. So when you roll a die, what can you possibly get? Well, you can get anywhere from 1 through 6. So in that case, sample space for that rolling a die would be 1, 2, 3, 4, 5, 6. Because you don't really get any number smaller than 1 or any number bigger than 6. Right? And it's only the natural number that you are going to get. So that's a sample space for an experiment which is rolling a die. However, each individual result could be 3, could be 5. What are those? We call that outcome, right? Each individual result is an outcome. If you collect every single possible outcome together, that's a sample space, okay? All right, so everyone got that, right? Sample space, outcome is each individual result. If you collect every single possible result, that becomes sample space. Okay, event. Now, what's an event? Event is any combination of outcome. They usually use uppercase letter like A or E, or another common uppercase letter that we usually use is E. E for an event, right? E for an event. So, you know, I mean, if you read it carefully, I mean, it says everything here. Event is what? Any combination of outcome. It could be a single outcome. It could be two outcomes together. It could be three outcomes. It could even be all possible outcomes. That could be an event. So, for example, if the experiment is flipping one fair coin, right? You flip a coin once. Then, you know, if you flip a coin, what can you possibly get? You can either get head or you can either get tail, right? So what would be the sample space for this case? Sample space would be head or tail, right? Now, they say event A might be getting at most one head. I mean, if you flip a coin once, you can, you know, maximum H is just going to be 1H. So what would be the probability that when you flip a coin, it's going to be one head, getting one head case? Well, that case probability of event, I mean, what do you think this P stands for? Probability of an event A. And who decide what this event is going to be? I mean, you decide what this event is going to be. You know, if you want to figure out the probability of that event. In our most realistic case, I mean, the question will define the event. You know, the textbook will tell us an example with particular event, right? So in that case, if you flip a coin, what's your chance of getting H? Well, 1/2, right? 1/2. Okay. probability of any outcome is the long-term relative frequency of that outcome. What does that supposed to mean? Well, you know, it's like this. If you flip a coin, do you really get exact 50% chance to get H all the time? That means like you flip a coin 2 times and you're going to get 1 H and 1 tail. Well, not really. Sometimes that you get, you know, 2 H or 2 tail, right? So when we say probability of getting 1 H is 1/2, that means we are talking about the long-term relative frequency of that outcome. Well, we'll talk a little bit more about this later, right? Okay, probability are between 0 and 1, right? Probability are between 0 and 1. What does that mean? Probability of any possible event, it's gotta be bigger or equal to 0 or less than equal to 1, like that. 1 in percent is going to be 100%, right? So, you know, technically speaking, I mean, sometimes we say something like, oh, I am 200% sure that this will happen. You know, technically that's an incorrect sentence. You can't have a chance probability that's more than 100%. You know, I'm 110% sure, something like that we say. You know, that's not really a correct sentence. If you're 100% sure, that means it's a certain event. It will happen no matter what, right? You don't have to, I mean, you cannot go anywhere beyond 1 or 100%. At the same time, can you have a probability that's equal to 0? Yes, you can have that, right? That means that event is never going to happen. You know, something like this. When you roll a die, what's your probability of getting number 7? Well, there's no 7 in a die, right? You either get 1 through 6, so there's no 7. So chance of getting 7 is going to be equal to 0, right? And probability that's equal to 1, that means it's a certain event, it'll always happen, right? So if you want to say like, what's the probability when you roll a die, it's going to be, the number that you are getting is going to be less than 7? Well, 100%. You will always get, when you roll a die, number less than 7, right? So anywhere from 1 to 6, right? Okay. Event and probability event. Event and probability of an event. So, for example, if you flip a fair coin repeatedly, let's say, you know, 20,000 times, then the relative frequency of head approach 0. It's like, you know, if you flip a coin, you know that you have half chance either get head or tail, but that doesn't guarantee that when you flip 2 times that you're going to get exactly 1 head and 1 tail, right? It's not always the case. Sometimes you get HH, sometimes you get TH, sometimes you get HT, sometimes you get TT, right? So it's not exactly always 1 head and 1 tail. However, if you flip a coin, let's say 200 times, then you roughly get 100 H, 100 tail. You roughly get. It's not exactly going to be 100 though, right? I would bet on it. It'll probably get a little less than here, a little more than here, or something like that. However, you know, If you flip a coin 2 million times, for example, that means, you know, you get 1 million each, roughly speaking. The actual probability is going to approach the theoretical probability, which is half head and half tail, right? Okay, that's that. Equally likely means that each outcome of an experiment occurs with the equal probability. I mean, simple example would be a fair coin. You get exactly equal chance of getting head or getting tail, right? That's equally likely outcome. What else could be or equally likely event? Well, you either roll a die. When you roll a die, the face value is going to be 1 through 6. And they have an exactly equal chance to get any one of those numbers, right? Unless the die itself is it's not really proper one, right? So if you, and the coin too, right? Sometimes it's not evenly weight distributed coin, then it's not a fair coin, that you may not get the exact half chance of getting head and half chance of getting tail, right? So equally likely means it has the exactly same chance. All the outcome in that experiment has exactly same chance of getting picked, right? Okay. So how do you actually calculate a probability of an event A? You know, we talked about flipping a coin. We said getting H was 1/2, but how did we know? Well, because when you flip a coin, sample space was H and T, so you have two possibilities, and one of them was head, so probability of getting H was 1/2, like that, right? So that 2 was what? That was number of outcome in a sample space. In this case, there's a 2. And this number on the top, right here, is the number of outcome in an event A. In our event, this event was what? Getting 1H, right? All right, so let's talk about this example right here. For example, if you toss a fair dime and fair nickel, I mean, don't get too confused. I'm talking about just, you know, if you flip a coin, two coins, right? One's dime, one's nickel, doesn't really matter. If you toss 2 quarters, it's the same deal, right? So the first coin, whatever that you toss, could be H. In this case, the second coin that you toss is also H. That's why you write HH. This one right here, the first coin could be the tail, but the second coin is the head. This case is the first one was a head, second one was a tail. This is the case, the first one is a tail, second one is a tail, right? So, and that's all possible case. If you toss a coin 2 times, or if you toss 2 separate coins, and this is, you know, all you can get, right? So sample space has how many outcome? 4 outcome, right? 1, 2, 3, 4. So let's define this event A as getting exactly 1 head, right? Event A, that they are going to define this event A as getting 1 head. So out of these sample space, right? Out of this sample space, which one is 1 head case? This one right here, and this one right here. right? This is a two-head case, this is a two-tail case. So one head case that we're gonna call that event as an event A. Event A is equal to HT and TH, right? And we know that all these outcomes are equally likely outcomes. So there are 4 equal chances, and 2 of them, which is namely HT and TH, is the event that has one head case, which is just going to be 1/2, which is 0.5. 0.5 is what? 0.5 is same thing as 50%, right? You need to put one more zero there, get rid of that point and make it 1%, like that, right? 50%. Okay. So, example, let's say you roll a fair 6-sided die. They say sometimes 6-sided, they just say simply die sometimes. So when you roll a die and you are going to get 1 through 6 like that, and you define, or someone define their event E as what? Rolling a number that is at least 5. Now, at least 5, does that include 5? Yes, could be 5 or higher. That's what they mean by at least, right? So this event E is going to have 2 outcomes, 5 and 6. And what's this? This is the S, the sample space. So sample space has 6 equally likely outcomes, and our event E, which is at least 5, has 2 outcomes. So you simplify, and this is what you get, right? 1/3. So, I mean, I'm sure that everyone knows how to simplify this, right? You look at this 2 as 2 times 1. You look at this 6 as 2 times 3. And if you have same number, you cancel out. So you have 1/3 left, which is what we have here. So, for event F, right, they're going to define another event F is rolling an even number, right? So even number F, even number, what are the even number? 2, 4, 6. So you have 3 outcomes right here over 6. Again, 3 over 6. You look at this 3 as 3 times 1. You look at 6 as 3 times 2. You have same 2 cancels out. Then you have 1/2, just like that, right? Okay, so, I guess example could be something like this. You are rolling a fair die with the number 1 through 6. Find the probability of E where the E is defined like this, rolling a number at least 5. Then what do? You figure out what do you have in E, figure out the probability, and figure out the answer, just like that, right? Same thing here. You're rolling a die and find the probability of an event F, which is you're getting an even number. That's right here, right? Just like this, right? Could be our quiz question, right? Could be not even number, but like an odd number. If it's odd number, let's call that event as O. What are you thinking inside this O event? Well, odd number from this would be what? From this sample space would be 1, 3, and 5, right? So probability of getting odd number is also 3 over 6, which is 1/2. Just like that. Okay. Event and probability of event. Well, the basic idea is not that different from our previous slide, right? So it's almost the same deal. Let's talk about this one. So use the following information to answer the next 6 questions. In a jar of 150 jelly bean, right? So there's a jar here, and inside jar there's a bunch of jelly bean. There's actually 150 in there. Now, how many of them are red? Out of this 150, 22 red. How many of them are yellow? 38 yellow. How many of them are green? 20 green. 28 purple. 26 blue. So they have, I guess, 5 different colors. Oh, and the rest are orange. Rest are orange. So let's think about it. Total has to be 150. If you add 22, 38, 22 red, 32 yellow, plus 20 green, plus 28 purple, plus 26 blue, plus, unknown number of orange. That should add up to 150, right? So if you add all this, then what do you get? Adding these two would be what? That's 60. Adding this more would be 80, right? Adding this more to 80 would be what? 108, right? 108 with this would be 134, right? 134. So if you add all this, it's 134. Let me just double check just to make sure that I'm not making any mistake. 28 plus 26. Yes. So how many orange do we need? So plus this should be 150. So we need 16 orange, right? Orange should be 16, right? Just like that. So that if you have 16 added, then all together it's going to be 150, just like that, right? Okay, so let's define our event B as out of this jelly bean jar, you pick one jelly bean. What's the chance that it's going to be a blue, right? How many blue do we have? 26. So this must be 26 out of 150. All right, just like that. And that's the answer for this question. Now, what about G? G is getting a green jelly bean. I mean, we know green 20. So 20, 150. Now, should you simplify? Answer is yes and no. If I want you to simplify and put your last answer in the simplified form, I will say it in the example that please reduce your final answer to the simplest form. If they don't mention anything like that, then you can just leave it like this. Okay, getting an orange. All right, orange that they didn't give you the number of orange initially, but we were able to figure it out. It's a 16. So it's a 16 over 150. I mean, you get the idea, right? The rest is easy. Purple jelly bean, 28. So 28 out of 150. And red jelly bean, red, 22. So 22, 150. And yellow 38, 150. Right? So, and there's a answer right there, right? Okay, so I hope this is straightforward for most of us, right? All of us, actually, right? So 150 jelly beans. Out of that, we have all these different colors. It could be M&Ms, it could be jelly bean. You know, we don't really care, right? But I hope you know how to figure out these kind of probability, right? Okay. Probability of outcomes that are not equally likely, right? Not equally likely. So, you know, we assume that when you flip a coin, we assume that we have 50% chance to get head, 50% chance to get tail. But, you know, in Europe and Belgium, they tested one of those European coin, and out of 250, trial, meaning, flipping a coin, they actually obtained 56% of head and 44% of tail, which means the coin that they tossed, it wasn't a fair coin, right? The weight distribution was not exactly half and half, right? So, sometimes it's not exactly 50-50, right? Outcome itself. Okay. Let's talk about this one right here. Probability that a particular knee surgery is successful is 85%, 0.85, 85%. So what does that mean? That means if you have one patient who have a knee problem that needs a surgery, the chance that the surgery goes successfully is 85%. But the question is though, find the probability that not one knee surgery, but two knee surgery are successful, right? Find the probability that not only one, but two knee surgery is successful. That's actually 72. Should I say the probability equal 0.7225. But how did we get this? Well, you have to wait just a little bit longer to actually learn how to figure out this probability, right? We'll definitely get to this part. So what they are trying to say in here though, when you have a surgery like this knee surgery, you don't have 50% chance of success or fail, right? Sometimes, probability of success is much higher in this case than probability of failure, right? So sometimes that you have to deal with a different probability with the not equally likely outcome. So, when you are calculating this two knee surgery successful case, I mean, if you really just talk about whether it's successful or not successful, your sample space is going to be one of these, right? The first, you can also figure out the sample space using what's called a tree diagram. Let's say this is S is just a sample space. First knee surgery could be success or could be failure, right? After the first surgery, the second surgery also could be success or fail. If the first one was a failure, the second could be success or failure. So if you consider this case, this is S case. If you consider this case, this is SF case. If you consider this case, this would be FS case. If you consider this one, this is FF case. Just like that, right? So you have 4 possible cases, which is listed in here. However, we should be a little bit careful because each probability of this sample space are not the same, because remember, the success and the failure, they have a different probability from the beginning. This is not equally likely outcome, right? This is not equally likely outcome, right? So if you have 2 knee surgery, chance of getting 2 knee surgery as success case is not 1/4 or 0.25, right? 1/4. It's not like that, right? It's actually this. And we will learn later how to actually calculate this probability. But for us for now, we would like to know, check at least that sometimes the outcome is not equally likely, then you cannot simply count how many are there and figure out the probability. You can only do so if you have equally likely outcome, right? Okay. Or event and end event. Now, again, this is introduction course chapter for this probability chapter. So later on, we are going to learn how to actually deal with this or probability and end probability in detail. But the basic concept is exactly the one that we know. Now, when we have this example set A, let A be 1 through 5. Let B be 4 through 8. If you say A or B, that means anything in A or anything in B altogether, right? But if it has to be A and B, that means it has to be in A, but it has to be in B at the same time. And we can see that this 4, 5 is in A, but it's in B as well. So A and B is going to be 4 and 5, these two set like that. Okay. So, or means it could be here, it could be here, or it could be here. Right? That's or. I mean, that's or that we know, right? And means it has to be in here, but at the same time, it has to be in here too. That's and, right? Complement of an event. A complement of an event A prime. We read this as A prime. Now, some other reference book, you would also see A to the little c on the top, and we also read this as A complement. But in most textbook, you'll see this little prime right there, and we read this in A prime, which refers to a complement of an event A. So what's a complement of an event A? Well, complement event A consists of all outcomes that are not in A. For example, let's say this is all outcome sample space S, right? Because sample space means what? It should contain every single outcome. In the sample space, you have 1, 2, 3, 4, 5, 6, like that. Now, let A, event A be 1, 2, 3, 4. So this, that we're going to call this as A. That's A. Then what should be A complement? Whatever in the whole, but not in A. which is this, right? This 5 and 6 it's in S, but it's not in A. So we call this as A complement, or we can also say A prime, same thing. So what would be the probability of getting A, meaning anywhere between 1, 2, 3, 4? Well, out of total 6, we have 4 chances. What's the probability of A complement then? Well, you have 5 and 6, which is 2 of them out of 6. So when you add these, you are going to get 1 all the time. Right? You are going to get 1 all the time. So that's a concept of a complement, right? That's a concept of a complement. Okay. Okay. Conditional probability. Again, conditional probability, we are going to study this topic in details later on. But for now, we just introduce this conditional probability. Conditional probability, we denote this as this bar right here, this bar, B. And we call this as a conditional probability. So what is this? We want the probability of A. However, we have a condition. What's the condition? B has to happen first. That's conditional probability. Let me repeat that again. We are looking for a probability of an event A. However, we have a condition. What's the condition? Event B has to happen first. So that vertical bar right here, we read this as given. That's how we read it. So probability of A given B. Conditional probability of A given B. How do we write it? We write it like that. See that bar right here? That's a given part. Probability of A given B. What does that really mean? This probability of A given B is probability that we want event A will happen, but we have a condition. Event B must happen first. Right? Must happen first. And that's a conditional probability. Right? So we calculate probability of A from reduced sample space of B, right? That's a basic concept. But for now, it's just good enough to know that this is given that we read, and this symbol really means for conditional probability. And the meaning of conditional probability is right here. We want the probability of A, but we have a condition. What's the condition? B has to happen first. That's the condition. Okay. So, very simple example. Let's say fair die toast 1 through 6. We define our event A as 2 and 3. We define our event B as 2, 4, 6. If you want to calculate conditional probability of A given B, right? A given B. What's the probability of A? Just the not conditional, just the normal probability. Probability of A is 2 out of 6, right? 2 out of 6? Because you have 2 chances out of 6. But let's say if you want the probability of A, but we have a condition, it has to be in B, or B has to happen first. So you are not picking A from the whole sample space. You are trying to count the A within B. So in B, you look for A. In B, how many 2 or 3 do you have in here? You have one of them. So in this case, it's going to be 1 out of 3. I mean, this reduced to 1/3 too. Is it always the same? No, not always the same. It just happened to be the same like this. Right? It just happened to be the same like that. But it's not always the same. Right? In fact, in many times it's very different. So probability of A given B, basic idea is like that. Then you are looking for the probability of A, but you have a condition. What's the condition? B has to happen first. Okay, that's the wrap for this lecture.